Hello and welcome to my talk on a paper which is called Learning to Reflect, a unifying approach for data-driven stochastic optimal control. This research was conducted during my PhD at University of Mannheim. It's joint work with Søren Christensen from Kiel University and Claudia Strauch from Aarhus University. So the basic problem that we are interested in is a stochastic optimal control problem where we are given a scalar process X, some control Z, and a cost function CT, which determines the long-term average costs associated to controlling the process X by Z, as in a limit appearing here on the right-hand side. In general, one is then interested in determining on the one hand the minimal cost C star and the respective optimal control Z star within the class of admissible control strategies. In particular, when the optimal control is of reflection type, the optimal cost can usually be expressed as the minimizer of a cost representing functional FC in some complex ZK, whose dimension is either 1 or 2, depending on whether we are considering 1 or 2 side reflections. The optimal control is then determined by the optimal reflection boundary theta star. Now, the fundamental assumption in stochastic optimal control is that the dynamics of X are known, and hence the theoretical solution can be calculated or at least numerically approximated. We, on the other hand, want to see what happens when we drop this assumption, such that we have to estimate the optimal reflection boundary under uncertainty on the characteristics of the process. To this end, we have the following simple but important observation that if we are given some estimator f hat of the cost representing functional fc based on some collected data of the uncontrolled process x up to time t, and as an estimator of the optimal reflection boundary, let theta hat be the minimizer of the estimator f hat, then the additional cost triggered by using the estimated boundary compared to the optimal one is of the same order as the subnorm risk of the estimator of the cost representing functional. As a first fundamental step for developing data-driven controls with quantifiable regret rates, we must therefore be able to construct a good estimator with respect to the subnorm risk. In this paper, we are investigating the issue of such data-driven controls, now more specifically for 2 different optimal control problems. One is based on continuous diffusion process and one on Levy processes, so in particular jump process. But although the problems are quite diverse, we demonstrate that at the core, data-driven strategies can be developed with the same non-parametric tools based on ergodic theory of Markov processes. So for the first problem we are considering, we have a continuous ergodic scalar diffusion at hand with drift B and diffusion coefficient sigma, whose invariant transition density is given by this formula here involving both the drift and diffusion coefficient as well as a normalizing constant CD sigma. We now reflect the process at some boundary points psi and theta, where the controls u psi and d theta are the local times of the reflected process at the boundary. And we're now concerned with the long-term average cost of such a reflection strategy given by this expression here, which involves on the one hand some continuous cost C and also linear cost QU and QL associated to applying the control. Now this cost representing functional has a closed form expression given by Alvarez in 2018, which perhaps not too surprisingly, on the one hand involves the ergodic continuous costs expressed as this integral here with respect to the invariant distribution and essentially ergodic costs coming from the applying the controls. As I said at the beginning, the goal is now to construct a good non-parametric estimator of FC, and of course, looking at the expression for FC above, natural estimator in this case is a plug-in estimator where we just replace the invariant density by an estimator hat row, which we choose to be a kernel type with bandwidth HT. And as it turns out, the subnorm convergence rate of this estimator is of the same order as the subnorm, so of the cost estimator of the cost functional is of the same order as the subnorm convergence rate of the kernel invariant density estimator hat row, which we must therefore analyze. And this is done with some general tools for statistics of continuous time Markov processes that we developed in another paper with Lukas Trottner and Claudia Strauch. And there it is shown that when we have a long time control on the transitional behavior of Markov process form of exponential ergodicity, together with a short time control in form of a heat kernel bound of the estimator, the invariant density can be estimated at rate square root T over T with square root log T over T with respect to subnorm risk when we choose an appropriate bandwidth, which is independent of the assumed degree of Holder smoothness beta of the invariant density. Thus, The estimator of the invariant density is adaptive and therefore also truly data-driven in nature, which is important to us. Now, with the observations that we've made before, this allows us to conclude that the excess costs associated to the data-driven strategy are of order square root log t over t as well, at least when we make some standard assumptions on the coefficients of x guaranteeing exponential ergodicity and the heat compound. The problem that naturally arises with this strategy is that we assume that we can observe data of the uncontrolled process for the estimation of the reflection boundary, but did not take into account that this observation period causes costs from not controlling the process during this time. But on the other hand, if we try to estimate the optimal reflection boundary based on controlled data, we cannot expect this procedure to converge because the process cannot explore areas that are relevant for inferring its characteristics. So we therefore face an exploration-exploitation type problem. And we resolve this by splitting up the timeline into exploration and exploitation periods, where during the exploration periods, we leave the process uncontrolled and use the gathered data for estimation of the optimal reflection boundaries, which are then used to control the process in the subsequent exploitation period, which is depicted here, where blue paths represent exploration and green paths exploitation. And the purple boundaries are updated according to the data gathered in the exploration periods. The central statistic for the strategy is now the time st spent in exploration periods until the time t. And we show that when this time is of order t to the power of 2/3, then the regret of the data-driven strategy is of order square root log t over t to the power of 1/3, and therefore incurs some additional loss compared to the previous result, where we assumed that we can observe the process without cost. In the paper, we exactly specify what we mean by st is of order 2 to the power of 2/3, and also show that there also exists a strategy which satisfies these assumptions. So let us now come to the other control problem that we consider, which is impulse optimal controls of a Levy process X, which we assume to be upward regular. So it immediately hits the upper half line when it started in 0, and we assume it to have finite and strictly positive means, so that eventually diverges to plus infinity as time progresses. We control the process by impulse type controls S, which consists of subsequent stopping times tau n and points zeta n, where the process is reset at time tau n to the reset point zeta n. Now we are concerned with maximizing the long-term average reward of such strategy, which in some sense is of course equivalent to cost minimization as for the previous diffusion case. The reward associated to resetting the process to zeta n at time tau n is determined by a value function gamma, and the long-term average reward is the long-term average of the expected cumulative rewards obtained from applying controls. And we denote the optimal long-term average reward in the class of impulse strategies by V star. For the theoretical solution, the essential process is the ascending ladder high process H, which we obtain from X by a time change with inverse local time at supremum. And this process H is then the subordinator with the same range as the running maximum of the process X, and therefore tracks the maximum, although on a different time scale that is determined by local time. The reason why this process appears is the following. If we are looking at the reward obtained from the impulse strategy that resets the process to a point X after it has passed the value X plus epsilon, then it is given, then the reward, expected reward is given by this difference quotient here on the right-hand side. So when we let epsilon go to 0 and choose a scaling of local time such that the means of X and H are the same, then the right-hand side converges to the extended generator of H applied to the reward function gamma at X by Dinkel's formula. And essentially letting epsilon go to 0 is optimal, since if we look at the problem formulation, the control problem formulation, there are no costs associated to applying the controls, so that we end up with a reflection type result actually, which is that under some technical assumptions, the optimal reward is given as the maximizer of the generator function f, and the corresponding argument theta star can then be interpreted as an optimal reflection boundary, where reflection for us means a sufficiently fast approximating impulse control strategy. So as before, we now need to find a non-parametric estimator of this generator function f with fast soup norm convergence. But we are not faced with an exploration-exploitation type dilemma because of the spatial homogeneity of the Levy process, which essentially allows simultaneous estimation and reflection by undoing the controls such that we can use a greedy strategy that continuously updates the optimal reflection boundary based on our estimator. And this greedy strategy is here described by theta hat. But now the real challenge is how to build such an estimator, because local time at the supremum cannot be observed, even when we have a full record of our process available. So we have to find some trick to build an estimator. And the way we do it is that we rewrite the generator functional of H in the following way, such that on the right-hand side, we have expressed the generator functional in terms of a measure mu, which consists of an atom at 0 of size drift of H over the mean of x1 and the Levy density away and the Lebesgue density away from 0 given by the tail Levy measure of the ascending ladder high process also scaled by the Levy mean. And so what's the interpretation of this measure mu, and how can we use this to our advantage that we have now re-expressed this generator functional? And the right way to look at it is via the overshoots of x. So an overshoot OX over a level x is the amount by which the Levy process surpasses this level x at first passage. So since this is the same as the overshoot of a running maximum of x, it is also the same as the overshoot of the ascending ladder height process h over x. So there is a natural connection between these two objects, and we can use it to draw inference in h, since if we now use the levels x as time parameter, the process constructed from the overshoots OX can be shown to be a Feller-Markov process, and mu is its invariant distribution. So the generator functional above can be written in terms of an integral with respect to the invariant distribution of this Markov process O, and therefore a first natural estimator is a mean estimator based on overshoots collected up to a spatial level capital Y. To analyze its subnorm convergence behavior, we now want to employ the same statistical techniques as in the diffusion case, and therefore need to find conditions on the overshoot process that guarantee exponential ergodicity. This was done in another paper together with Leif Döring, where we show that under light tail and regularity assumptions on the Levy measure, we have both exponential ergodicity as well as exponential beta mixing of the overshoot process. And this now allows us to conclude with the same Markov statistical techniques as before, that the spatial estimator converges at rate 1 over square root y, where again y is this spatial level up to which we observe the process. Of course, we want to find a way now to transfer this result to a temporal estimator, so to an estimator based on observations up to a fixed time capital T instead of up to some random hitting time Ty. The way we do this is by replacing the level capital Y by the random value of X evaluated at T. And so then we obtain a temporal estimator, and its subnorm convergence rate can be analyzed based on the estimation rate for the temporal estimator and non-asymptotic concentration inequalities for the Levy process around its mean because of this fundamental inequality that we observe here above. In case of existence of p-th moments, a Markov inequality type argument yields then a convergence rate of almost square root t, which improves in the magnitude of p. And if we even assume bounded jumps of the process, then we can perform a Chernoff type argument using the infinite divisibility of x to improve the convergence rate to square root log t over t, which is the same rate that we observe for diffusion processes and which is typical for subnorm non-parametric estimation with continuous observations. And by the same argument, by the argument using spatial homogeneity of the level process from before, we therefore also obtain that the greedy strategy at theta t yields a regret of the same order. So that's it from me. Thank you very much for watching, and I hope to see as many of you as possible in the live sessions. Bye-bye.